Hello, my name is Bill Robbins. Today I'm going to talk about wide bandgap devices for power electronics. The topics I'm going to cover are shown in the outline below. I'll first discuss why silicon devices are going to be inadequate for future applications. I'll then talk about the wide bandgap materials that will offer improved devices. I'll do some comparisons between silicon and wide bandgap devices. I will then talk about a relatively new power electronic device, the gallium nitride high electron mobility transistors, and then finally I'll conclude with what present-day wide bandgap devices capabilities are and a look ahead. This chart shows the approximate power capabilities of present-day silicon devices. It's a complicated three-axis plot. On this side I have blocking voltage capability up to 5 kilovolts. Along the horizontal axis I have the on-state current capabilities out to about 3,000 amps, and along this axis, starting from the back and coming forward, if you like, sort of out of the page, I have the switching frequency capabilities. The highest power devices are thyristors and related devices. However, they're quite slow. And so they appear here at the back of the presentation. GTOs and some of the related devices like integrated gate, commutated thyristors, and emitter turnoff thyristors have somewhat higher switching frequency capabilities, but they're not quite as high a blocking voltage or on-state currents. IGBTs are sort of the workhorse of modern-day power electronics. Their capabilities span a wide range of blocking voltages, on-state currents, and switching frequencies up to several tens of kilohertz. To go beyond about 100 kilohertz, about the only device that is capable in the silicon family are MOSFETs, and they have capabilities up to about a kilovolt and frequent and current capabilities up to 50 or perhaps 100 amps. But their switching frequency capabilities go out to a megahertz and higher. The reason why I make the statement that silicon devices are inadequate for future applications is the technology is fairly mature. I expect only minor evolutionary improvements to occur in the future. Unipolar silicon devices like MOSFETs and Schottky diodes are used for high frequencies up to hundreds of kilohertz and voltages up to perhaps 1,000 volts. Bipolar devices like SCRs and IGBTs, PIN diodes are used for higher voltages, 1 to 20 kilovolts, but their switching frequency capabilities are significantly lower. Furthermore, silicon devices are limited to junction temperatures of no more than 150 to perhaps, if you're optimistic, 200 degrees centigrade. However, power electronic applications are pushing the boundaries to higher voltages, higher operating frequencies, higher temperatures, and higher efficiencies, in some cases all simultaneously. Silicon device usage in these future applications is going to be increasingly difficult and expensive. Fortunately, wide bandgap power devices offer potential solution. These devices are better than silicon power devices, especially for high voltage applications. They are faster, have lower losses, and higher operating temperatures. Now, wide bandgap devices operate by the same physical mechanisms as silicon devices, and their device geometries are quite similar to corresponding silicon devices. Hence, the better performance that we get out of wide bandgap devices is due to the superior material properties, which I'll discuss in a bit more detail in a moment. Wide bandgap materials that are currently of interest include gallium nitride, silicon carbide, and perhaps in the more distant future, diamond. The reason for the interest in these wide bandgap materials is sort of summarized in this table of material properties. I list 4 materials, including silicon carbide, gallium nitride, and diamond. Bandgap. Wide bandgap materials are significantly higher bandgaps than silicon, 3.2 for silicon carbide, 3.4 for gallium nitride, and 5.5. I list the relative dielectric constants, and they're similar. Diamond is about a factor of 2 smaller. Their saturated electron drift velocities are similar, diamond having the highest saturated drift velocity. Thermal conductivities. Silicon is only about 1.5 watts per degree centimeters. Silicon carbide is 3 to 4 times better. Gallium nitride is a couple of times better. Diamond is significantly better. And this higher thermal conductivity means it's easier to get heat that is dissipated in these devices to the outside surface of the device. The intrinsic carrier densities of the wide bandgap materials are significantly smaller than those of silicon, and this implies then higher operating temperature capabilities. Mobilities of all these materials, particularly for electrons, are quite similar. Hole mobilities are also similar. The main factor that plays into why semiconductor materials that have wide band gaps make better devices is in the breakdown field strength. Silicon is only about 300,000 volts per centimeter. All of the rest are at least an order of magnitude larger, and as we're going to see a little bit later, this is the prime factor that makes the wide bandgap materials superior devices for power electronic applications. For example, let's consider a simple example of calculating the blocking voltage capability of a PN junction. I'm assuming a one-sided step junction. It's not too difficult to show that the breakdown voltage is proportional to the square of the breakdown field strength divided by essentially the doping density. And the drift region thickness has to be greater than twice the rated breakdown voltage divided by the breakdown field strength. And if you look at the table here, I'm assuming equal breakdown voltages for all 4 types of materials. And what we see is doping density in silicon has to be quite small, 6 times 10 to the 14th. The other materials can be a couple orders of magnitude higher, which means significantly lower on-state losses. The width of the drift region, or length if you like, is pretty long in silicon, 67 microns. All of the others are at least an order of magnitude smaller, with the smallest being in diamond. Smaller drift region lengths, of course, also mean smaller on-state losses. Going forward, if we do a comparison of the on-state resistances, the figure of merit is usually the on-state resistance times the area of the current that is flowing through that resistance. The area of the device through which the current is flowing. This is the so-called ohms per square. And if the drift region is the dominant factor in on-state losses, it's fairly simple to show that an approximate formula for the losses for the on-state resistance is given by this formula. It's proportional to the square of the breakdown rating and divided by the cube of the breakdown field strength. If we normalize that to silicon and assume the same breakdown voltage for all types of devices, similar devices made out of the 4 different materials, the on-state resistance ratio in silicon it's 1. Silicon carbide is about 10 to the minus 3. In gallium nitride it's 4 times 10 to the minus 4, and in diamond it's 4 times 10 to the minus 5. Again showing why the breakdown field strength is the most important thing in determining on-state resistance and thus switching losses, conduction losses. If you do a comparison for a bipolar device, one can show approximately that the ohms per square of the on-state resistance is given by the formula that I'm showing here, breakdown voltage divided by breakdown field strength, and 1 over the approximate excess carrier density. If we normalize to silicon and assume the same breakdown voltage and same excess carrier density, again I calculate the ratios, and again the wide bandgap materials show superior performance. Higher operating temperatures of the wide bandgap devices are basically due to the fact that wide bandgap means that the intrinsic carrier densities are much smaller. Here I have a table of different junction temperatures, and for each of the 4 major materials that we're considering, I show the intrinsic carrier density. And even at elevated temperatures, as high as 1,000 degrees, silicon carbide has an intrinsic carrier density of 3 times 10 to the 14th. Diamond is about 1.7 times 10 to the 13th, whereas silicon is 10 to the 18th. The problem with this is, as the intrinsic carrier density gets larger than any of the doping levels, you're essentially shorting out the p-n junction. The p-n junction reverse saturation current is proportional to Ni squared, and so it's going to increase significantly as the junction temperature increases, even if you haven't reached the value of intrinsic carrier density that shorts out the p-n junction. In addition, the drift regions develop a positive temperature coefficient, leading to possible thermal runaway when Ni at the given temperature exceeds the drift region doping density. In practice, the temperature limits are going to be probably significantly lower and set by packaging, interconnect and reliability issues, phase changes, thermal stresses, and the temperature limitations of other components that are used in conjunction with the power device itself, such as capacitors or inductors. Switching speed comparisons. If we do a bipolar comparison, I show here a PN junction, PIN diode, forward bias with some current I. The excess stored charge in the drift region is approximately I times the carrier lifetime. The drift region length has to be approximately or somewhat smaller than the diffusion length, which is the square root of the ambipolar diffusion constant times the carrier lifetime. If you invert this equation, I have 1 here now for the carrier lifetime, and the ambipolar diffusion constant is defined in the next equation. And the drift region length is also given here by twice the breakdown voltage divided by the breakdown field strength. Putting all that together, you can show that the excess stored charge is given by the current times these other parameters. And the thing to note is that it's proportional to the square of the breakdown voltage and this over 1 over the square of the breakdown field strength. If we compare a silicon diode with a wide bandgap device, one can show that for the same current and the same breakdown voltage, and assuming the mobilities are the same, the ratio is basically of the stored charge in the wide bandgap material divided by the stored charge in the silicon device is proportional to the square of the breakdown field strength of silicon divided by the breakdown field strength of the wide bandgap device. And this is going to be much less than 1. And so the wide bandgap diode will switch much faster than a silicon diode using the same drive circuit. And similar reasoning would apply to IGBTs and other bipolar devices such as GTOs and thyristors. If we wanted to estimate a comparison for unipolar devices like MOSFETs, here's a single cell of a MOSFET which shows all of the parasitic capacitances that make up the device and contribute to the switching time capability of the device. If we assume that we're talking about, say, a very simple buck converter circuit, then we can make some analytical estimate if we wanted to of what the switching times would be. I'm not going to do that in this particular presentation, but I would point out that all of these capacitances are what are a major determinant of the switching speeds of the device. And these capacitances are proportional to the overlap area that I've defined here, which is the approximately the area through which current flows through the drift region. The area of a drift region for a wideband device is much less than that of a silicon device if you assume the same drift region resistance. And if we're thus using the same driving circuit, the WBG device will switch much faster than silicon. The conclusion is wide bandgap devices are faster than comparable silicon devices, primarily because the much larger breakdown field strength allows the cross-sectional area of the device, of the wide bandgap device, to be much smaller than that of a comparable silicon device, thus much less capacitance, or in the case of bipolar, much less stored charge. If we can make a qualitative comparison between conduction and switching losses, conduction losses in bipolar devices are dominated by the on-state resistance, and if we assume identical devices, that is breakdown voltage and cross-sectional area, and excess carrier density, the smaller drift region length, means that the wide bandgap device is going to have lower losses. In bipolar devices, switching losses are going to be also much less in the wide bandgap device because of the much faster switching time. Conduction losses in unipolar devices like MOSFETs, again, the smaller drift region length of the wide bandgap device means lower conduction losses. And also, we can have much higher doping levels in the drift region in the wide bandgap device, and that further contributes to lower losses, conduction losses. Switching losses in the unipolar devices in wide bandgap, again, is going to be significantly less because of the faster switching times. And that's ultimately traceable to the fact that the device is smaller, particularly the area of the drift region. One of the new devices that's possible with wide bandgap materials for power electronics is the GaN HEMT transistor, HEMT standing for High Electron Mobility Transistor. This slide shows the basic structure in a simplified manner of a so-called lateral gallium nitride HEMT transistor. The device is made starting with a substrate of either silicon carbide, or sapphire, and then MOCVD or MBE is used for device fabrication. One of these two techniques is used because it gives you great control over the vertical thickness of the various layers. So on top of the substrate we grow 1 to 2 microns of semi-insulating gallium nitride, then about a 30 angstrom thick layer of insulating or intrinsic aluminum gallium nitride, and then another 30 angstroms or so of heavily doped N-type aluminum gallium nitride. And then windows are opened up for the source and drain contacts, which are ohmic contacts, and then also a rectifying contact for a Schottky barrier contact for the gate. The drain and source metallizations have to be specially picked to get the ohmic contact, and similarly for the gate metallization. High voltage capability requires that the distance between the gate and drain be 5 to about 15 microns. Right now, 600 to 900 volt blocking capability devices are commercially available with on-state resistances of 10 milliohm and ohms or less. The device which is shown here is normally on, but normally off devices have been demonstrated in a lab by making structural and doping changes. The on-state operation of the device occurs when you have zero gate to source voltage, because this is a normally on device. In that situation, the electrons which are in the N+ aluminum gallium nitride near the interface are able to diffuse across and into the intrinsic gallium nitride. And the reason for that is the average energy of the electrons in the N+ aluminum gallium nitride are higher than that in the gallium nitride layer, and so they just naturally will diffuse across. This forms an accumulation layer at the interface between the spacer layer and the aluminum and the intrinsic gallium nitride, and the density of the electrons here is so high that it's sometimes called a two-dimensional electron gas. Numbers that are often quoted are 10 to the 13th electrons per square centimeter. The accumulation layer or two-dimensional electron gas is a very low resistance channel between the drain and source. And the device, as I've already shown, is a normally on device. The spacer layer is essential because what it does is it separates the free electrons in the accumulation layer from the aluminum gallium nitride, which is heavily doped. And this is essential because without the spacer layer, the ionized donors that are right at the interface would influence the mobility of the electrons in the two-dimensional electron gas and greatly lower their effective mobility. But by having the spacer layer here, we greatly diminish the influence of those ionized donors, and so the electrons in the accumulation layer or two-dimensional electron gas take on essentially the same mobility as electrons in the intrinsic gallium nitride bulk, and that is significantly higher than the mobility in the N+ aluminum gallium nitride by a factor of 4 or 5 or more. Vertical GaN devices are under development that in principle should have much lower on-state values than the lateral devices. However, those are not yet ready for prime time, and so further development is going to be required. In the off state, what one has to do is reverse bias the gate to source junction as I've shown here. And if the negative gate to source voltage is larger than the so-called pinch-off voltage, this will create a depletion region that I'm showing here that will block the current through the two-dimensional layer, and so no current will be able to flow from the drain to the source. The main requirement for a large voltage rating is that the distance from the gate to the drain be large enough to accommodate the lateral growing depletion layer without the depletion layer boundary hitting the drain metallization and thus implementing punch through. In order to do that, field plates are usually required in order to shape the electric field properly within the depletion region, but I haven't shown the field plates for simplicity. There are other secondary factors like interface traps and the possibility of vertical breakdown between the drain and the substrate if the substrate is grounded, as the source might be, but that can also affect and lower the breakdown voltage capability. But this is getting into details that are beyond the scope of this particular presentation. Well, now we come to a question: if these approximate model calculations have any validity, then there probably ought to be a variety of wide bandgap devices commercially available, and that is indeed true. I did a quick search using Google and came up with the following list of devices: a MOSFET normally off enhancement mode using gallium nitride, 600 volt breakdown, 52 millimos for the on-state resistance, current capability 36 amps. Another MOSFET, this time silicon carbide, up to 1700 volts was available, had an on-state resistance of 1 ohm and 3 amp capability, at 1200 volts, 25 milliohms, on-state resistance, 60 amp capability. And you can perhaps read the rest of the chart. There's a bipolar junction transistor at 1700 volts, 45 amp capability, a thyristor, silicon carbide at 6500 volt blocking, 6 millimos, 80 amp capability, normally on JFET silicon carbide, similar capability as the MOSFET enhancement mode, Schottky diode at 1700 volts, 25 amp capability, forward voltage 1.8 volts. A PIN diode silicon carbide at 8000 volts, 2 amps. A half-bridge module made out of enhancement MOSFETs, silicon carbide, 1700 volts, 225 amp capability. I use the asterisk up here after the word commercially because there are part numbers for all of these, but it may be that they're fairly preliminary and it may be difficult to obtain some of these devices that are so-called commercially available. Looking at more demonstration devices in the research laboratory, here is a 10 kilovolt PIN silicon carbide diode at 100 amps per square centimeter, which corresponded in this case to about 50 amps flowing. The forward voltage was about 3.7 volts, and it goes on up from there. The blocking voltage capability, when you went out to a reverse voltage of 8000 volts, the leakage current was someplace in the neighborhood of a few hundred microamps. This chart shows the forward bias capabilities at various temperatures: 100 amps per square centimeter, 400, 2000. Here are the various temperatures, and the thing to note is all of these track very well together as a function of the forward voltage, and thus paralleling these as a function of temperature would seem to be possible. Turn-off behavior is quite fast. Here we're going from 100 amps per square centimeter at a forward voltage of 4 volts with a dIdt of 330 amps per microsecond, and it turns off starting from this point something on the order of about 200 nanoseconds. And so we're talking about a fairly fast turn-off for this high voltage device. And it's showing it at different temperatures, and it seems to be relatively independent of temperature. Here are some other examples of devices that I found doing a quick search. Junction barrier Schottky diodes at 10,000 volts, a PIN diode at 4,500 volts, 180 amps, 3.2 forward voltage, a vertical MOSFET at 10,000 volts, 10 amps, an N-channel IGBT at 12,500 volts, on-state resistance of 5.3 millimoles, a commutated GTO at 4,500 volts, 120 amps, a bipolar junction transistor in silicon carbide at 4,000 volts and 10 amps, a normally off JFET and gallium nitride, 100 amps at 600 volts and 9 millimoles, and you can read the rest. There's even a diamond Schottky diode at 10,000 volts, but I couldn't find any other information about it. So what does this all mean? I think we've convincingly demonstrated that wide bandgap devices are fundamentally superior to silicon. The basic reason is the 10x or more larger breakdown field strength that enables faster switching with lower losses. The larger bandgap enables higher operating temperatures, and the larger thermal conductivity provides the ability to dissipate more power in the device without exceeding the temperature limitations. There are a variety of commercial silicon carbide devices available, and they're going to dominate power electronic applications probably above 1,000 volts in the future. Gallium nitride devices are theoretically somewhat better than silicon carbide, but lag in availability, basically because vertical gallium nitride development has been hampered by a lack of large, inexpensive gallium nitride wafers. From a fundamental viewpoint, diamond would be the best material for power devices, but the lack of large, inexpensive single crystal wafers is hindering their development. In my estimation, it's going to be 10 or 20 years before there's any diamond devices commercially available, and maybe longer. It's going to be a function of the technology development in making large single crystal diamond wafers. Thank you for your attention.